Welcome to Shanti-Peace for Mathematics. In my previous video, we have talked about the chain rule for derivatives, which tells you that if you have a z, which is a function of two variables x and y are the functions of t, then you will have a z is a function of t, and the derivative of z with respect to t can be represented as del z by del x into dx by dt plus del z by del y into dy by dt. Now in this video we will talk about if z is a function of two variables, that is f of xy, and x and y both of them are functions of another two variable, let's say u and v, and if this x and y are differentiable, that means this f function is differentiable with respect to x and y, and this x function is differentiable with respect to u and v, and y is also differentiable with respect to u and v, then you can talk about the derivative of z with respect to u and v. And what should be the partial derivative of z with respect to u in terms of the partial derivative of z with respect to x, partial derivative of z with respect to y, partial derivative of x with respect to u, partial derivative of x with respect to v, partial derivative of y with respect to u, and partial derivative of y with respect to v. What should be the partial derivative of z with respect to u, and what is the partial derivative of z with respect to v in terms of this partial derivatives, that we will discuss in this lecture. The same argument I can give for if you have a function as three variable, that means w is a function of x, y, z, and this x is a function of two variable, y is also functions of two variable, and z is also functions of two variable. Then originally your w is a functions of two variable u and v. So what should be the partial derivative of w with respect to u and the partial derivative of w with respect to v? That also we will discuss in this lecture. So before that I need some of the theorem, so let us discuss that. So the statement of the theorem says this: let z is equal to f of xy be a differentiable at xy. Also x is equal to x of uv and y is equal to y of uv are differentiable function. Then prove that z is a differentiable at uv. Here what we have is z is a function of two variable, that is x and y are the functions of u and v. So that is the situation we have. And what should be the if z is a differentiable with respect to x and y, and this x and y which are the functions of u and v, they are the differentiable with respect to uv, then the question is z is also differentiable with respect to uv. Let us try to prove this statement. So here given that x is equal to x of uv and y is equal to y of uv, both are differentiable at any point uv, thus the differential of xy is given by dx, that we have talked in my previous video, that is del x by del u du plus del x by del v dv, and dy we can write as del y by del u du plus del y by del v dv. Now what is given is x is equal to x of uv is differentiable. So by definition what we can have of a differentiability, that is delta x is nothing but the xu delta u, xv delta v plus delta u epsilon 1 delta u delta v plus delta v epsilon 2 delta u delta v, where this epsilon 1 and epsilon 2 tends to 0 as delta u delta v tends to 0. This is by definition of differentiable function. as x is a differentiable function at point UV, so we'll have this. And similarly, y is also differentiable. So we have for that delta y is equal to yu delta u plus yv delta v plus delta u epsilon 1 delta u delta v plus delta v epsilon 2 delta u delta v. Since this is epsilon 1 and epsilon 2 are already used, so we'll use here the epsilon 3 and epsilon 4, and this epsilon 3 epsilon 4 tends to 0 as delta u delta v tends to. What else is given is z is a function of xy which is a differentiable. So for that also we can write the same thing. So also given that z is differentiable at xy. So therefore delta z is equal to zx delta x plus zy delta y plus zx epsilon 5 delta x delta y plus delta y epsilon 6 delta x delta y, where this epsilon 5 and epsilon 6 they will tends to 0 as delta x delta y tends to 0. Now here delta z is there and delta y is there. So in this equation, if I call it this is as equation 1, that is the delta x value. Delta y value I may call it as equation 2, and this delta z value if I call it as equation 3, and if I substitute this delta x and delta y in this equation 3, so using 1 and 2 in 3, we have delta z is equal to zx inside delta xu delta u plus xv delta v plus epsilon 1 delta u delta v into delta u plus epsilon 2 delta u delta v into delta v. This is over, plus it is zy. So zy into, and delta u delta y is there. So according to the same way, yu delta u plus yv delta v plus epsilon 3 delta u delta v into delta u plus epsilon 4 delta u delta v into delta v, plus these two terms are already there. Here also I may write down what is the value of delta x and delta y, so that also we need to write there, plus epsilon 5 delta x delta y. Just assume that instead of delta x we have substituted the value, then instead of delta y also we have substituted the value. Since this is very lengthy, so I am not writing here, but instead of this delta x coming here, that the same value should come here. So that is xu delta u, xv delta v, epsilon 1 delta u delta v into delta u plus epsilon 2 delta u delta v into delta v plus epsilon 6 delta x delta y. Here is also we are doing the same thing, that is yu delta u yv delta v plus epsilon 3 delta u delta v delta u plus epsilon 4 delta u delta v into delta v. Now this whole quantity I may just write down as taking this quantity together and taking this quantity together. We may write as this is zx into xu delta u plus xv delta v plus zy yu delta u plus yv delta v. Now what is the remaining term? That is this zx will multiply to this quantity, zy is multiplying to this quantity, and this epsilon 5 is multiplied to whole of them. That I can write down whatever the terms of delta u contains. So whatever the coefficients of delta u contains, that I am writing first. So that is plus delta u into some function of delta u delta v, and whatever the coefficient of delta v we write down as a function of phi, that is phi 2, where this phi 1 delta u delta v you may write as zx epsilon 1 plus zx epsilon 2 plus epsilon 5, and inside bracket or in multiplication of epsilon phi is all this bunch that we can write, that is xu delta u plus xv delta v plus delta u epsilon 1 plus delta v epsilon 2, and phi of 2 in the similar manner we can write as zy epsilon 3 zy epsilon 4 plus z6 and whole bunch of this. So, and you just note that this phi 1 and phi 2 will tends to 0 as delta u delta v tends to 0. So, what we can say is this phi 1 and phi 2 will tends to 0 as delta u delta v tends to 0. That can be follows from this, because this epsilon 1 and epsilon 2 is also tending to 0. Epsilon 3, epsilon 4, epsilon 6, epsilon 5 are also tends to 0 as delta u delta v tends to 0. And so from this what we can say is this is delta z. So from this what we can say is z is a differentiable function with respect to uv, and what is this quantity? It is the total difference of z you will have, so that will gives you dz equal to zx dx plus zy dy. If you take the limit delta u delta v tends to 0, we'll have this, and that's complete the proof that if your z is a function of two variable x and y, and this x and y are the functions of two variable u and v, and if your z is a differentiable with respect to x and y, and this x and y are the differentiable function with respect to uv, then z is also differentiable function with respect. Now we have the next is the chain rule for partial derivatives, which tells you the same thing. If you have x which is a function of uv and y is a function of uv, they have the first order partial derivatives exist, and if z is equal to f of xy is differentiable at point xy, and this xy is actually a function of uv, then z also have the first order partial derivative as a composition function, that is of this form, and del z by del u is written as del z by del x into del x by del u plus del z by del y into del y by del u, and del z by del v is written as del z by del x into del x by del u plus del z by del y into del y by del u. This formula is very easy to remember. If you just remember this T diagram, the T diagram is look like in this manner. Z is there. Z is a function of two variable x and y. Z is a function of two variable. That's why you can talk about its partial derivative. So that's why it is del z upon del x, and this is del z upon del y. And this x and y are the functions of two variable u and v. You can talk about the partial derivative of x with respect to u and v. So that's why it is del x upon del u, del x upon del v, and this is del y upon del u, del y upon del v. Now if you want the first formula, then you have to go along the path where u is there. So u is at the two places, so that's why you have to go along this path first and then this path, and the second you have to go in this path and then this path. Delta z upon delta x into delta x upon delta u, that is the first quantity you will have. And if you go along this path, another path, that is delta u upon del y, delta z upon del y, and delta y upon del u will gives you this quantity. And if you go on the second path, that is first move from this one and secondly move from here, that is the you have to approaching v here, so that's why you are moving from this and then this, so you will have this formula. This formula is easy to remember. Let us talk about now proof of this formula. So given that z is differentiable with respect to xy, and x is a function of uv and y is also a function of uv, they are also differentiable with respect to uv. By previous theorem, what we can say is Therefore, z is also differentiable with respect to uv. So that's come from the previous result, that is z is a differentiable function with respect to uv and x and y are the differentiable function with respect to uv, and therefore z is also differentiable function with respect to uv. So we can talk about its differential. Therefore, we write differential of z with respect to u and v as dz is equal to del z by del u into du plus del z by del v into dv. Now, x is a function of uv, is differentiable, so that's why we can talk about a differential with respect to u and v. So that can be written as dx is equal to del x upon del u into du plus del x upon del v into dv. Same way we can write for y in the similar manner. dy is equal to del y by del u du plus del y by del v dv. And you have z, which is a function of originally function of x and y, and so for that we can write as differential with respect to x and y, that we can write as dz is del z by del x into dx plus del z by del y into dy. Now you have here dx and dy, and that same value we have here, that is dx and dy. So we'll just substitute these two values here in this formulas. That's why we can have this is equal to del z by del x. So inside bracket we have the value of z, which is del x upon del u du del x upon del v dv plus del z by del y is there, which is this, into dy. The value of dy is here, so that's why it is del y by del u du plus del y by del v dv. You just simplify this, and if you write down the terms of du together and dv together, so we'll have this is del z by del x into dx by du plus del z by del y into dy by du into du plus del z by del x by del v plus del z by del y by del v dv. This is nothing but the dz. If I call it this is as a double star, and you have that is one equation, this is known as a star. So if you compare this star and double star, you just notice that del z by del u and del z by del v is comes to this quantities. So that's why we'll have del z by del u equal to del z by del x into del x by del u plus del z by del y into del y by del u, and del z by del v equal to del z by del x by del v plus del z by del y into del y by del v. These two formulas are known as the chain rule for partial derivatives in given as this situation. Let us try to solve some of the examples here. So the first example, z is equal to e power xy is there, and x as a function of uv is given as 2u in plus v, and y is a function of uv. The question is to find out del z upon del u and del z upon del v using chain rule. So first, whenever a partial derivative example is there, you have to plot the t diagram. So the t diagram says that z is a function of two variables x and y according to the given situation, and x and y are the functions of uv. So that's why if you want to calculate z as a function of 2v, you have a two path. So that's for this is del z upon del u can be written as del z upon del x into del x upon del u plus del z upon del y into del y by del u. So you are just going along first this path, that is del z upon del v and then del z upon del u. Secondly, you are going to this path. Now you just see that this del z upon del x, the derivative of e power xy is e power xy into y. The derivative of x with respect to u, that is 2 from this, plus derivative of z with respect to y, it is e power xy into x, and the derivative of y with respect to u, that is 1 upon v. If you simplify this, e power xy is common out, so you will have 2y plus x upon v. You may convert this whole quantity in terms of uv, then you will have it is as e power, the value of x is 2u plus v into u by v. So this is 2uv by 2uv plus by v. This is actually you will have e power 2u plus v into u upon v. This is 2u upon v plus 1, and this 2uv plus 2uv will become 4, so that's why you will have this. In similar manner, you have del z upon del v, which is del z upon del x upon del v, plus del z upon del y upon del v. So z you will have e power xy, so that's why it is y e power xy. X you will have 2u plus v, so that's why it is 1. Del z upon del y, as per the same way, it is x e power xy. Del dy by dv, y is u by v, so it is minus u upon v square. To simplify this will gives you e power x into y is common out, y minus x u upon v square. If you substitute the value of x and y, so this will gives you 2u v into u upon v, inside bracket u upon v minus 2u plus v into u upon v square. So if you simplify this, u upon v will get cancelled out, and you will have the finally minus 2u square upon v square into e power 2u plus v into u upon v. That is the final answer, that is del z upon del v you will have. Let's have the another example. Given that w is e power x y z, here your w is a function of 3 variable, x is equal to 3u plus v, y is equal to 3u minus v, and z is equal to u square v. So your w is a function of 3 variable here, that is yz. So as I already told you that whenever the partial derivatives example is there, first thing is to plot the t diagram. So this w is a function of 3 variable, and this x and y are the functions of uv according to the given situation. So now u at the 3 places, and the question is to calculate what is del w upon del u. U is at the 3 places, so you have to go along the 3 path. The first one is this, the second one is this, and the third one is this. So this del w upon del u has a 3 quantity here, that is del w upon del x into del x upon del u, that is via this path, plus del w upon del y into del y by del u, that is via this path, plus del w upon del z into del z upon del u, that is via last path that we have here. Now the question is to calculate these quantities. So del w upon del x, according to this it is yz e power xyz, because the derivative of e power xyz is e power xyz, and the derivative of xyz is yz with respect to x. Now this is del x upon del u, so the derivative of this with respect to u will gives you 3, plus this is will gives you with respect to y, so it is x z e power xyz. The derivative of y with respect to u is again 3, plus xy into e power xyz. The derivative of z with respect to u is 2uv. Further, you can just substitute the value of uv here. by simplifying or by computing the value of uv from in terms of xyz, and you can write down your answer in terms of uv. So that finally what we are writing is the function in terms of xyz as 3yz plus 3xz plus 2uvxy. This is your final answer, which is in terms of xy and uv. Same way you can calculate del w upon del v. Also we have here three paths, that is v at the three places. So that's why you will have three paths here, that is del w upon del x into del x upon del v, that is via this path. Del w upon del y into del y by del v, that is the second path you will have here. And the third one, that is del w upon del z into del z by del v. Now we need to calculate what is the each and every quantity. So this is the derivative of e power xyz with respect to x will gives you yz into e power xyz. Your x is 3u plus v, so according to that the derivative of this is 1 plus xz e power xyz. So the value of y is 3u minus v, so that's why it is minus 1, and e power xyz into xy, the value of z you will given as u square v, so that's why it is u square. And you just common out this e power xyz out. Finally you will have yz minus xz plus xy u. That's the answer for this. Now we'll have the next example. Let us given that w is x square plus y square plus z square. So this w is a function of three variable, and you have given as x as rho sine phi cos theta, that is y is equal to rho sine phi sine theta, and z is equal to rho cos phi. So this is nothing but the spherical coordinates that it is well known to you, and the question is to find out what is del w upon del theta and del w upon del rho. I am giving you as an exercise that del w upon del phi you can calculate yourself. I will calculate this too here. So the first thing you need to do is to plot the t diagram. Here you will have w, which is the function of three variable according to this situation. So that's why it is x, y and z. According to this situation, the x, y, z are the functions of rho, theta and phi. So it is rho, theta and phi. Y is also a function of rho, theta and phi. Z is also a function of rho, theta and phi. So now if you want to calculate what is the del z upon del theta, then you have to reach at three places, because the theta at the three places, here, here and here. So you will have three paths. The first path is this, the second path is this, the third path you will have this. So that's why you will have three terms here. So first y at this path, so that is del w upon del x into del x upon del theta plus del w upon del y into del y upon del theta plus del w upon del z into del z upon del theta. What is del w upon del x? According to this it is 2x. Del x upon del theta, that is the derivative of this with respect to theta, will gives you minus rho sine phi sine theta plus w del w upon del y, which is 2y, del y by del theta, that is rho sine theta sine phi cos theta plus 2z del z upon del theta. This z does not contain theta, so that's why the derivative is 0. So finally you will have rho is common out, sine phi is also common from this quantity, 2 is also common. If I can take this 2 common out, so inside bracket you will have x sine theta minus x sine theta plus y cos theta. But if you just substitute the value of x and y here, then you will have 2 rho sine phi. The value of x you will have, it is rho sine phi cos theta, and sine theta is already there, so that's why it is sine theta, plus rho sine phi sine theta, and cos theta is already there, and you just note that both the term will cancel out, so finally you will have 0, that is del w upon del t. Next we need to calculate what is del w upon del rho. So for that, here we'll have 3 paths because rho at these 3 places. So you have to go along this path and then this path. Here you will have going to this path and then this path, and here you will have this. So it is del w upon del x and del x upon del rho, del w upon del y upon del rho, and so on. So this is del w upon del x into del x upon del rho plus del w upon del y into del y upon del rho plus del w upon del z into del z upon del rho. So what is del w upon del rho? It is 2x del x upon del rho, so that is sine phi cos theta plus 2y sine phi sine theta plus 2z into cos phi. Now substituting the value of x, y and z here, we will have, this is 2, the value of x is rho sine phi cos theta, this is the value of x, and sine phi cos theta is already there, so it is square here, plus 2 rho sine phi sine theta, and sine phi sine theta is already there, so that's why this, plus 2 rho cos square phi. Now the rho is common out, 2 is common out, and from these 2 terms sine square phi is common out, so that's why you will have 2 rho sine square phi cos square theta plus sine square theta plus 2 rho cos square phi. So this is 1, and cos square theta plus sine square theta, so 2 rho is also common out into 1, so it is 2 rho. Now I am giving you as an exercise to compute del w upon del phi. You may calculate it yourself. Let's have another example. W is a function of xy plus yz, so that is the w is a function of 3 variable x, y and z, and you have given is y is a function of x, that is sin x, and z is e power x. So originally what is the happen is your function w is only one variable x, because if you substitute the value of y and z here, then this w is only a function of z. So that's why the question is to calculate what is dw upon dx. So let us plot the t diagram here. So here w is a function of 3 variables, that is x, y and z. You note that this y is a function of x variable and z is also function of x variable, and you just note that this x at the 3 places, so you'll have 3 terms here, and you may write that is as the w upon dx as del w upon del z, because there is no other path towards this, so only we'll have this, plus del w upon del y, so we are moving along this path. Here the w is a function of 3 variable, which is, that's why it is partial derivative, and here on this path y is only function of x, that's why it is dy by dx plus del w upon del z into dz by dx in the similar manner. Now let us calculate this quantity del z by del x. According to that, it is y plus del w upon del y is x plus z. Dy by dx is cos x. Del w upon del z, that is derivative of this with respect to z, will give you y, and this is e power x. If you can substitute the value of y and z here, so everything will convert into x. So the value of y, it is given as sin x. So this is sin x plus x plus e power x cos x plus sin x e power x. So finally you will have x cos x plus sin x plus e power x cos x plus sin x. So this is the final answer you will have. I will highly recommend that you may go through with the lots of examples based on chain rule. Some of the examples as an exercise given in my lecture notes. I will also prepare one of the more video on this chain rule for only based on the examples. Let us recall what we did in this lecture. In this lecture, we will talk about the chain rule. If you have the function w, which is given as the function of two variables x and y, and this x and y are also given as a function of two variables u and v, then you can talk about the partial derivative of u or w with respect to u in the two path, and in the similar manner you can talk about the partial derivative of w with respect to v. So if you like this video, please press the like button. If you have any comment, suggestion or a question, please drop down in a comment box below. Till then, bye bye, sayonara.